1. A brilliant mind once likened the cosmos to the grandest gallery of cosmic art, and it's hard to argue with that sentiment when you take in the breathtaking scenes our telescopes unveil. Each snapshot reveals a universe so immense, so jaw-droppingly vast, that it defies every boundary we might try to impose on it, stretching beyond comprehension, shattering any tidy framework we devise. The first quasar ever spotted, a blazing supermassive black hole at the heart of a far-off galaxy, exemplifies this grandeur. Sitting over 2 billion light-years away, the light we catch from it has been on a journey for just under 1.99 billion years. Not quite the full distance, thanks to the universe's expansion stretching the space between us and that distant beacon. Imagine an observer peering at the Milky Way from such a stretch. If they could somehow squint hard enough to spot Earth, they'd see our planet as it was nearly 2 billion years ago, a snapshot frozen in cosmic time. Back then, Earth was shaking off the great Huronian Glaciation, a 300 million year icy grip that ended 2.2 billion years ago. Oxygen levels were just starting to creep up, hitting a modest few percent for the first time. Life was stirring, with eukaryotes, cells packing specialized organelles, making their debut. Photosynthesizing critters like cyanobacteria and blue-green algae were hanging on, trimming carbon dioxide down to a sliver of the atmosphere. The early Earth, once thick with methane and ammonia, had shed that primordial cloak. A chemical peek at the air would scream alive, but nothing complex, nothing hinting at intelligence or diversity yet. Earth was just another rock hosting simple, thriving life forms. That faraway observer, if curious enough, might also notice Saturn's bare profile, no rings in sight. None of the gas giants had them yet. Those iconic features spun into being a bit later. Now, let's flip the view. Imagine gazing at Earth from another galaxy, say Galaxy 3295 spotted in 1960. Racing away from us at about 35% the speed of light, this galaxy sits roughly 5.6 billion light-years off today. Its light starting out 4.5 billion years ago. What would an observer there see? In a youthful star cluster within the Milky Way, about 27,000 light-years from its core, a brand new star system popped up sometime in the last 60 million years. Around a cool, young star swirl 4 inner rocky worlds, one freshly minted, with a hefty moon from a colossal crash. Beyond lies an asteroid belt, 4 gas giants, and a sprawling fringe that'll one day earn names like Kuiper and Oort. Yep, it's our solar system in its infancy. Back then, Pluto was just the second biggest player in the Kuiper belt, outranked by Triton. A world later snagged by Neptune. Earth's early vibe probably featured a volatile atmosphere heavy with hydrogen, helium, water vapor, ammonia, and methane, much like Mars and Venus at the time. Life might have been sparking on any of these fledgling planets, but to an outsider, no clear signs would stand out, no markers of biology reshaping air or land. It'd look like any other rocky speck, unremarkable, lifeless. From that distant galaxy, no one could guess if this water-rich orb would ever host clever beings. The farther out you look, the less sense it makes to spy on Earth. Beyond a certain stretch, peering at the Milky Way means peering at a time before our planet, our star, or our system even existed. With the observable universe spanning 46 billion light-years, only 0.18% of today's stars and galaxies, out of about 2 trillion, could have glimpsed the Milky Way when Earth took shape. That leaves a staggering 1.9 trillion galaxies clueless about our little home, and us about them. Humans, the only advanced thinking species we know of, have been around a mere 200,000 years. Just a handful of nearby star systems, thousands at most, might catch wind of our tech-savvy ways. Only those in our galaxy, maybe a few beyond, could even register we're here. Yet in that brief blip of collective time, we've probed vast swaths of the universe, back to the Big Bang's fiery dawn. For a lone species on a pale blue dot adrift in this cosmic sea, that's no small feat, right? Sub to our channel, give this a thumbs up, good vibes, and see you next time. Speaking of cosmic voyages, let's spotlight NASA's Voyager 1, which in 2012 crossed the heliopause, a bubble of charged particles and magnetic fields hugging the sun. It became the first human-made craft to breach interstellar space, launched in 1977 alongside its twin, Voyager 2. It's been on an epic trek ever since. By 2020, Voyager 1 was zooming toward the unknown at about 61,000 kilometers per hour, the fastest thing we've ever built and the farthest from Earth, clocking in at 24 billion kilometers. Light takes nearly a day to bridge that gap. Since liftoff, it's cruised past Jupiter and Saturn, skimmed the Kuiper Belt, and pierced the heliosphere's edge, beaming back priceless data all the way. Now in interstellar turf, it's set to brush past other star systems down the line. First up, post-solar system, AC plus 79388, or Gliese 445 for short, since it lacks a snazzy name like Sirius. What do we know about this star? Let's dig in. Gliese 445 sits 17.6 light-years away in Camelopardalis, not tracing the constellation's outline but within its bounds, near Polaris. It's a textbook red dwarf, the Milky Way's most common stellar breed. These dim, petite stars dominate our galaxy's roster, but need a telescope to spot, like Gliese 445 on our sky. Their faint glow stretches their lifespans far beyond the sun's, burning slow and steady. Of the 30 stars closest to us, 20 are red dwarfs, Proxima Centauri, the sun's nearest neighbor, being a prime example. Gliese 445 formed like any main sequence star, a dust and gas cloud clumped under gravity, spun up and fused at its core once temperatures hit the mark. Red dwarfs max out at 50% the sun's mass. Gliese 445 weighs in at 0.14 solar masses. Their smaller size means cooler flames, topping out at 3,500 Kelvin. Gliese 445 hovers around 3,200 Kelvin. That chill keeps them dim, sometimes 10,000 times fainter than the sun, sipping hydrogen so slowly their lives stretch to trillions of years. Unlike heftier stars that burn just core hydrogen before flaming out, red dwarfs use it all, inside and out, boosting their longevity. Telling them apart from brown dwarfs, failed stars too puny for hydrogen fusion, can be tricky. Brown dwarfs are colder, lighter, and sport clues like methane or ammonia in their air, surviving only at low temps. Lithium's another tell. Red dwarfs lack it, brown dwarfs don't. Red dwarfs often host exoplanets, though Jupiter-sized gas giants are rare. Their dimness makes planet hunting easier, a boon for missions like Kepler, 2009 to 2018, and TESS, since 2018, which scoured them for Earth-like worlds. Early on, scientists pegged red dwarfs as lousy for life, their tight habitable zones, where liquid water could exist, sit so close that planets catch harsh radiation or get tidally locked, one side roasting, the other freezing. Yet today, these systems are prime candidates for life. Proxima Centauri nabbed an exoplanet in 2016, another in 2019 beyond its habitable zone. TRAPPIST-1 boasts 7, some possibly life-friendly, red dwarfs. Longevity helps, offering stable homes for eons. Gliese 445. No planet spotted yet, but that doesn't rule them out. Red dwarfs may shine forever, well, a trillion years, but they'll eventually burn out, cooling into white dwarfs, just like the sun will. It's a slow fade to a common end. They're the galaxy's quiet champs, most numerous, longest lived, proving slow and steady wins the cosmic race. And it's toward Gliese 445 that Voyager 1 hurtles, though it won't arrive until around 40,272 AD, passing within 1.7 light-years. Here's the kicker. Gliese 445 is cruising toward us. In 40,000 years, it'll be just 3.45 light-years away, down from 17.5 now. Proxima Centauri holds the closest title for now, but it'll ustupete to Alpha Centauri, then Ross 248, and finally Gliese 445. What's next for Voyager 1? It'll graze the Oort cloud in 56,000 years, drift past GJ 686 and GJ 678 in 570,000 years. By then, a dead hunk of metal, its gear kaput by 2025. Voyager 2? It's trekking the other way, nearing Ross 248 in 40,000 years. A red dwarf in Andromeda, not the galaxy. Then Sirius in 296,000 years, 4.3 light-years off. Their finale's a mystery. Eternal wanderers pummeled by micrometeorites, or smashed by something bigger. They might outlast the solar system, and certainly us, their makers. That loops us back to the quasar's gaze. 2 billion years ago, Earth was a toddler, no hint of us. From 4.5 billion years back, it's a newborn system, life just a maybe. The universe's vastness dwarfs our brief stint, yet we've glimpsed its depths. Not bad for fleeting specks in the cosmic art show. Throughout most of the winter, piercing through the crisp, frosty air, 3 stars aligned in a diagonal row at the heart of a vivid rectangle gleam brightly in our sky, forming Orion's belt. This striking feature points northward toward the clusters of Hyades and Pleiades in Taurus, while southward it directs us to the dazzling canine star, Sirius, brightest in the night sky. Within Orion, just below and to the right of this belt, 2 massive stars stand out effortlessly, Rigel and Betelgeuse. While Betelgeuse often steals the spotlight, likened to an exhausted, wheezing old giant teetering on the brink of explosion, Rigel, also known as Beta Orionis, or the giant's left leg, tends to be overshadowed, which is a shame and hardly fair. Rigel ranks as the 7th brightest star visible from Earth, outshining all others in its constellation as a true supergiant. This radiant, hot blue star captivates with its stunning brilliance and is among the rarest gems in our galaxy. Located about 860 light-years from our solar system, Rigel blazes 47,000 times brighter than the Sun. Though it appears as a single point of light to the naked eye, the Beta Orionis system is far more complex, comprising at least 4 components: Rigel Alpha, Rigel Beta A, Rigel Beta B, and Rigel C. The 3 fainter companions, Beta A, Beta B, and C, are sometimes collectively referred to simply as Rigel Beta. There's also a 5th, dimmer star, more distant, and considered a potential part of this system. Rigel Alpha, the luminous supergiant, sits at a respectful distance from its trio of weaker companions, outshining them by a factor of 400. Rigel Beta, meanwhile, is a spectroscopic binary, meaning its dual nature is revealed not through direct observation, but by analyzing the spectral lines of its two stars, Rigel Beta A and Beta B, which are so close together that even powerful telescopes struggle to separate them. In contrast, Rigel Beta and Rigel C can be distinguished, but only with telescopes boasting exceptional resolution. The Rigel Beta C system takes roughly 24,000 years to orbit Rigel Alpha, while Beta A and Beta B whirl around each other every 9 days, and Beta and C complete their mutual orbit in about 63 years. Discerning the traits of Rigel Beta A, Beta B, and C is no easy feat thanks to their proximity. All three appear as bluish-white main-sequence stars with similar temperatures and estimated masses of about 4 times that of the Sun each. But let's shift focus back to the star of the show, Rigel Alpha, or simply Rigel. This brilliant, massive supergiant, glowing blue or bluish-white, is around 8 million years old with a surface temperature exceeding 12,000 Kelvin. Its radius stretches nearly 79 times that of the Sun, and its mass is calculated to be 21 times greater. Though often hailed as the brightest star within 1,000 light-years of Earth, Rigel's exact luminosity remains uncertain. Based on the widely accepted distance of 860 light-years, it's estimated to shine 120,000 times brighter than the Sun. Yet a recent study suggests it might be farther, 1,170 light-years, boosting its luminosity to 218,000 times that of our star. Classified as an Alpha Cygni variable, like the star Deneb, Rigel exhibits subtle brightness fluctuations due to non-radial pulsations, where parts of its surface contract while others expand. Stars like Alnilam share this category. Having exhausted its core hydrogen, Rigel has evolved off the main sequence, cooling and swelling to its current size. Its pulsations hint at a dynamic past. Perhaps it was once a blue supergiant turned into a red supergiant, then heated up again to reclaim its blue splendor. This isn't a fluke. Blue supergiants shrink rapidly as their surfaces contract, while their inner energy surges, raising their temperature and sometimes reverting red supergiants back to blue. Despite gaps in our understanding of Rigel's physics, its fate mirrors that of other massive stars. It will eventually erupt as a Type II supernova. As one of the nearest supernova candidates, its explosion could rival a quarter of the Moon's brightness. Thankfully, at its distance, Earth will remain unscathed. Rigel's spectrum, a standard for its class, reveals neutral helium lines, strong hydrogen absorption, and traces of heavier elements like oxygen, magnesium, and calcium. Rigel Beta, though bright enough to glimpse through small telescopes, is overshadowed by its proximity to Rigel Alpha. Separated by over 2,200 astronomical units, the binary shares the same proper motion as Rigel Alpha, orbiting each other in at least 18,000 years. Could such a multi-star system host exoplanets? Around 14 unconfirmed candidates orbit Rigel, but their detection is tricky amid the system's brilliance. Half are likely gas giants, while the rest, possibly rocky, are uninhabitable due to intense radiation. Orion, the great hunter or celestial warrior, has inspired myths across cultures, tying it to heroes, warriors, or demigods. Yet its tales are so numerous and tangled that Orion himself feels like a shadowy enigma. Still, his namesake constellation shines as the most recognizable and radiant in our sky, a Milky Way treasure trove brimming with extraordinary stars. Rigel, like many luminous beacons, has left its mark on history and culture, inspiring art and even lending its name to Antarctic landmarks, Rigel Reefs and Mount Rigel. The universe teems with mysteries, and one lies close to home, the Fermi bubbles, perplexing structures at our galaxy's core. Discovered in 2010 by the Fermi Gamma Ray Space Telescope, launched 2 years prior, these colossal formations stretch 50,000 light-years above and below the Milky Way's disk, an unusual orientation defying its spiral arms. At the galaxy's heart lies Sagittarius A/B, a supermassive black hole now dormant, but once, perhaps 300,400 years ago, more active. Scientists suspect it plays a key role in the bubble's origin. Picture it gorging on a massive object, heating the infalling matter until electromagnetic forces flung it outward as near light-speed jets, forming the bubbles we see today. Alternatively, a cataclysmic explosion millions of years ago, possibly a Seyfert flare, could have unleashed energy 1,000,000 times greater than the sun's lifetime output, impacting the Magellanic Stream, a gas trail from nearby dwarf galaxies. Visible in 2020 from Cerro Tololo Observatory, the bubbles glow with ionized hydrogen, expanding at 220 kilometers per second. The IceCube Neutrino Observatory in Antarctica detected high-energy neutrinos within them, hinting at cosmic ray interactions. Theories abound: proton collisions, electron boosts, or shockwave accelerations, but none fully explain the bubble's gamma-ray emissions. Future observations from Cerro Tololo may unravel this galactic puzzle, revealing what transpired millions of years ago. Until then, our galaxy proves it's far more complex and captivating than it seems. The star WHG64 was first identified in 1981, its name honoring the initials of its 3 discoverers, Westerlund, Olander, and Hedin, while G64 marks its position as the 64th entry in their catalog. This trio of Swedish astronomers compiled a list featuring over 500 potential M-class supergiant stars within the Large Magellanic Cloud, a dwarf galaxy orbiting our Milky Way. WHG64 stands out as a red supergiant enveloped by a vast donut-shaped nebula of gas and dust. With a radius spanning 1,500 to 2,000 times that of the Sun and a brightness hundreds of thousands of times greater, it claims the title of the largest and most luminous star in the Large Magellanic Cloud. This celestial find quickly revealed itself to be an extraordinary and enigmatic object. Though it doesn't dazzle in visible light, it more than makes up for it in the infrared spectrum. Astronomers attributed this quirk to a thick shroud of gas and dust cloaking the star, absorbing up to 75% of its emitted light. Between the 1980s and 1990s, researchers turned their spectroscopes toward WHG64, which earned the distinction of being the first extragalactic supergiant linked to astrophysical masers, sources of intense microwave radiation tied to objects like comets, stars, or, more commonly, molecular clouds. Spectroscopic studies uncovered masers of water, silicon monoxide, and most notably, hydroxyl, OH radicals, located just a few stellar radii from WHG64. Such masers signal that the star belongs to a specific group of evolved giants nearing the end of their life cycles, surrounded by opaque dust shells forged by powerful stellar winds. These shells trap the star's light, re-emitting it as infrared radiation, making these supergiants stand out infrared beacons. The OH masers' emissions, detected in the infrared range, confirmed WHG64 as a red supergiant in the asymptotic giant branch, AGB phase, a stage on the Hertzsprung-Russell diagram populated by low to medium mass stars in their twilight years. WHG64 boasts three remarkable traits: unmatched brightness among red supergiants in its galaxy, an unusually cool surface temperature, and an immense radius of at least 2,000 solar radii. Positioned 163,000 light-years from Earth, its size can't be measured directly. A 1986 study pegged its bolometric magnitude at 9.7, suggesting a luminosity 650,000 times that of the Sun. By analyzing absorption lines of titanium and vanadium oxides in its spectrum, scientists classified WHG64 as an M-type supergiant, characterized by a chilly surface temperature of about 3,200 Kelvin. Stellar evolution models suggested that only a star exceeding 2,000 solar radii could reconcile such brilliance with such a low temperature. Yet something about these observations didn't quite add up. What was off? A red supergiant shining like 650,000 suns should have originated as a main sequence star with a mass of 40 suns or more, according to theoretical predictions. But those same models insisted such a massive star should maintain a surface temperature no lower than 6,300 Kelvin, far hotter than WHG64's observed 3,200 Kelvin. This discrepancy puzzled astrophysicists, spurring a quest for clearer answers through deeper investigation. A breakthrough arrived in 2008 when Japanese astronomer Keiichi Oanaka and his team used Chile's Very Large Telescope to probe the star's infrared emissions. Their observations revealed a complex, thick toroidal dust shell, a cosmic donut, encircling WHG64. Viewed from Earth at a 20-degree tilt, we peer through a conical gap in this structure, catching light from one of the star's poles. This finding upended earlier assumptions that the star was uniformly dimmed by dust in all directions. With this new perspective, WHG64's properties were recalibrated. Its luminosity dropped to 280,000 times the Sun's. Its initial mass settled around 25 suns, and its radius shrank from over 2,000 to 1,730 solar radii, still a staggering 1.2 billion kilometers, or about 8 astronomical units. Placed in our sun's spot, it would swallow everything from Mercury to Jupiter, sparing only Saturn, Uranus, and Neptune. These revisions better align WHG64 with evolutionary models for a supergiant at roughly 3,000 Kelvin, though it's still edged into the forbidden zone beyond the Hayashi limit on the Hertzsprung-Russell diagram. Here, hydrostatic equilibrium falters. Gravity and the outward pressure from nuclear fusion no longer balance. This instability hints that WHG64 is nearing its end, likely to erupt as a supernova within a few thousand years, scattering debris into space much like SN 1987A, another large Magellanic Cloud supernova observed in 1987. Despite its looming demise, WHG64 is a cosmic youngster, less than 10 million years old, compared to our Sun's 4.5 billion years. Massive stars like it burn through their fuel. In a mere fraction of that time, too fleeting for life to emerge on any orbiting planets. One lingering question remains unanswered. Does WHG64 have a binary companion? Some spectral emission lines show radial velocities misaligned with the stars, hinting at a possible main sequence O-type star shining 100,000 times brighter than the Sun. If confirmed, this duo would be even more spectacular. For now, it's a tantalizing possibility without solid proof. Meanwhile, motion defines existence. Earth spins on its axis, completing a 360-degree turn in just under 24 hours. 23 hours, 56 minutes, and 4.09 seconds to be precise. This slight shortfall from a full day stems from our orbit around the Sun, nudging our position daily. We also circle the Sun at nearly 30 kilometers per second, covering 1 billion kilometers yearly, while our solar system races through the Milky Way at 220 kilometers per second, taking 250 million years per galactic lap. The Milky Way itself drifts within the local group, which glides through intergalactic space. From your couch, you're hurtling through the cosmos at speeds varying by latitude, 1,000 176 kilometers per hour at the equator, slowing to 0 at the poles. This rotation shapes life. Gravity strengthens at higher latitudes. Equatorial spin aids rocket launches, and tidal forces gradually stretch our days by 14 nanoseconds annually. Billions of years ago, Earth spun faster, with days lasting just 6 to 8 hours. Our galactic journey, tilted 60 degrees from our solar orbit, fluctuates between 208 and 237 kilometers per second. Amid this cosmic dance, WHG64 and Earth remind us of the universe's vast, restless beauty. Stay tuned for more cosmic wonders. The invisible pull of gravity between two hefty objects dictates how swiftly they rush toward each other under their shared influence. And as time passes, this speeding up causes these massive entities to shift positions rapidly across the vast expanse of space. Take our planet, for instance. Earth spins around its own axis daily while simultaneously tracing a path around the Sun, which itself is caught up in a larger journey, carrying the entire solar system along as it circles the Milky Way galaxy. Yet, even as these familiar movements play out, there are far grander cosmic motions unfolding in the background. I'm referring to the local group of galaxies, a collection that includes our Milky Way, which ranks as the second largest among roughly 60 galaxies bound together by gravitational ties. Leading the pack in size and mass is Andromeda, a galactic giant situated about 2.5 million light-years away from us, potentially weighing in at double the mass of our own galaxy. Andromeda's immense distance makes it impossible for us to track its positional changes with precision over the short span of a human lifetime, or even many lifetimes. Still, we can gauge how fast it's moving toward us along our line of sight. By examining the blue shift in its spectral lines, a telltale sign of an object approaching us, we've determined that Andromeda is closing in on our Sun at a pace of 301 kilometers per second. However, when we factor in the Sun's own trajectory and speed through the Milky Way, we find that the relative velocity between our galaxy and Andromeda adjusts to about 109 kilometers per second. This means we're on a collision course, one that will culminate in a spectacular galactic merger set to begin in roughly 4 billion years. Imagine an artist's rendering of this event, the Milky Way and Andromeda blending together, transforming our night sky into a dazzling display of intertwined stars and cosmic clouds. When that happens, the supermassive black holes at the hearts of these galaxies are expected to fuse into a single, even more formidable entity. With this, we step into the realm of the universe's most colossal scales. To explore these immense scales, we first need to map out the full array of galaxy groups, clusters, superclusters, and even larger structures that make up the cosmic landscape. Every massive object out there exerts a gravitational tug on us, drawing us closer, while regions with sparse material, those that have lost matter to denser zones around them, exert a pull far weaker than the cosmic norm. For our local group, the strongest gravitational influence comes from the Virgo supercluster, a sprawling collection of galaxies pulling us toward it at approximately 300 kilometers per second, relative to our other motions through space. On the opposite side of the sky, away from the Virgo cluster's core, lies a much less dense patch of the universe. While we call dense regions clusters, these thinner areas are known as voids, and the void near us effectively pushes us away at a similar speed, around 300 kilometers per second. With a hefty cluster tugging us from one direction and a near-empty void repelling us from the other, these forces align, driving our local group forward at a combined pace of about 600 kilometers per second. To get a true sense of our motion, we have to piece together all these elements: Earth turning on its axis, Earth orbiting the sun traveling through the galaxy, the Milky Way advancing toward Andromeda, and the local group being drawn toward dense regions while recoiling from sparse ones. By adding all these movements up, we arrive at a number that reveals just how fast we're really zooming through the universe right now. On average, our total speed through space clocks in at around 368 kilometers per second, with our path pointing toward the constellation Leo. This figure shifts slightly, by about 30 kilometers per second, over the course of a year, mainly due to Earth's changing position as it circles the sun. We confirm this through measurements of the cosmic microwave background radiation, the faint glow left over from the Big Bang, which appears warmer in the direction we're heading, Leo, and cooler in the opposite direction, Aquarius. We've also pinned down the sun's motion relative to this background at 368 kilometers per second, with an uncertainty of just plus or minus 2 kilometers per second, a remarkably precise estimate. Using the full suite of data we've gathered, we can calculate how the local group moves relative to the broader architecture of the universe. That comes out to 627 kilometers per second, give or take 22 kilometers, with our course set toward the constellation Centaurus. The wiggle room in that figure, plus or minus 22 kilometers per second, mostly stems from the challenge of accurately tracking the sun's orbit around the Milky Way's center, the trickiest part to measure with certainty. So let's sum it up. Nothing in the universe stands still. There's no such thing as a fixed, motionless, or solitary object. Everything is in constant motion. Today, we've uncovered how Earth journeys through the cosmos on every scale imaginable. Looking ahead, if we ever develop a more detailed chart of our galaxy, we might one day predict our future travels through space with a clarity that's hard to fathom now. I hope you've enjoyed this cosmic adventure. Give it a hearty thumbs up if you did, and always remember, space is endlessly fascinating. Now picture this. A new decade has just begun. The world teeters on the edge of monumental shifts, with synth-heavy beats pumping through speakers and movie fans eagerly awaiting the release of the sci-fi thriller Total Recall. Meanwhile, the scientific community buzzes with anticipation for the launch of the Edwin Hubble Space Telescope, a project delayed time and again for various reasons. Great expectations rest on its shoulders. It's tasked with answering, among other things, whether other planets lurk out there in the depths of space. Finally, in April 1990, the telescope lifts off to begin its mission. Peeking ahead more than 30 years, it's fair to say Hubble has largely lived up to the hype, delivering on those lofty hopes in spades. For thousands of years, our ancestors gazed up at the night sky, captivated by what seemed like countless twinkling lights. Many suspected these specks might be stars akin to our sun, just impossibly far away. But was our solar system unique? Did other stars have planets orbiting them? If so, how many, and what portion of those stars might host worlds? Above all, were any of those planets like our own Earth? Just over 3 decades ago, we started finding answers. We began spotting planets circling distant stars, uncovering entire planetary systems. Thanks to a blend of clever techniques, we've now confirmed more than 5,000 diverse worlds beyond our solar system, a tally that keeps growing. As often happens, these breakthroughs have been awe-inspiring and jaw-dropping, shedding light on some of our deepest questions about the cosmos. Yet, in true scientific fashion, those answers have sparked even more intricate mysteries. So, what have these distant planets taught us? First, let's nail down the term. The word exoplanet comes from the Greek exo, meaning outside or beyond. Early on, we called these far-off worlds extrasolar planets, but that was a bit of a mouthful. So over time, about 15 years into the discovery spree, it slimmed down to the snappy exoplanet, and it stuck. The key thing to grasp is that an exoplanet is any planet outside our solar system, whether it's a gas giant, a scorching hot Jupiter, or a rocky world with potential for life. To emphasize any planet beyond our sun's reach. This quest kicked off back in 1992, when two distinct approaches almost simultaneously began pinning down planets beyond our cosmic neighborhood. The first spotlight falls on a millisecond pulsar, PSR 125712, located in the constellation Virgo, about 2300 light-years from Earth. This pulsar is a neutron star, a compact remnant just 10 kilometers wide, with a mass 1.5 times that of the Sun. It's blisteringly hot, with a surface temperature of around 28,800 Kelvin, and it spins at a dizzying 9,650 rotations per minute. Formed between 1 and 3 billion years ago from the collision of two white dwarfs, it's a fairly typical example of its kind. What sets it apart, though, are its exoplanets, rare companions for such a highly magnetized stellar corpse. The initial discoveries in the system were PSR B257-12c and PSR B257-12d, later named Poltergeist and Phobiter, in 2015 by the International Astronomical Union. After mythological figures tied to dreams and beasts. Poltergeist is a solid planet, over 4 times Earth's mass, orbiting at 0.36 astronomical units, similar to Mercury's distance from the Sun, every 66 days, with a chilly surface temperature of 80 degrees. Phobiter, a super-Earth with 3.9 times Earth's mass and about 1.5 times its radius, orbits at 0.46 astronomical units every 98 days, clocking in at 104 degrees. 2 years later, in 1994, a third companion emerged, dubbed Draugr, after a Scandinavian undead myth. It's the innermost object circling the pulsar, with a surface temperature of 7 degrees and a mass twice that of the Moon, possibly making it the lightest known planet in the universe. I'll save the tale of how these 3 worlds formed and survived their star's explosive past for another day. Typically, such planets would vaporize under the million Kelvin heat and radiation of a supernova. For now, let's rewind to the discovery method. It was 1992, and no exoplanets had been confirmed yet. Scientists studying the pulsar noticed its regular pulses speeding up, returning to normal, slowing down, and normalizing again in a repeatable cycle. This consistent pattern suggested massive objects were at play. By analyzing the timing of these pulses, they deduced the masses involved and confirmed they were planets. A similar approach spotted periodic red and blue shifts in the light of other stars, hinting at hefty planets tugging their hosts back and forth in space. Though indirect, meaning they detected presence rather than directly observing the planets, these methods proved reliable, unleashing a cascade of discoveries that now number in the thousands. Today we rely on 5 techniques to hunt exoplanets and uncover their traits. First up is pulse timing. We've just covered this. It hinges on stars emitting regular periodic signals like pulsars. The steadier the signals, the easier it is to catch timing shifts caused by orbiting companions. If these stellar remnants have planets circling them, with periods shorter than our observation window, this method will spot them. Next is radial velocity, often called the stellar wobble technique. Here, an unseen planet and its star orbit their shared center of mass, causing the star to shift slightly. This only works if the planet is massive enough and close enough to its star to make a detectable impact. This approach nabbed 51 Pegasi b, the first exoplanet found around a main sequence star, 51 Pegasi, a milestone that introduced us to the hot Jupiter class of planets. Then there's direct imaging, arguably the most thrilling method, though it's fiendishly tough. It's the only way to capture light directly from an exoplanet itself. It works best for large, bright worlds far enough from their star to avoid being drowned out by its glare, yet close enough to Earth for our telescopes to see them. A standout find here is GJ 504b, just 57 light-years away, aged 100 to 200 million years. Still young, it offers a glimpse into planetary evolution. Infrared cameras reveal a deep pink hue, with fewer clouds than most gas giants we've observed. If we could visit, we'd see a world glowing dimly crimson from the heat of its formation. The transit method, meanwhile, is the most prolific and favored technique, though its first success came only in 2004. It involves tracking a star's light over time. If a planet crosses in front of it from our viewpoint, the star dims slightly. Repeated dips of the same size and timing confirm an exoplanet's presence. It's great for big, fast-orbiting planets, but only if the alignment of star, planet, and our sightline is just right. The first catch was a hot Jupiter 5,000 light-years away in Sagittarius. Finally, there's gravitational microlensing, effective when you're peering at a distant star and a massive object passes between you and it. Unlike transits, which need a planet close to its star, this relies on mass-bending space itself, altering the light of background objects. Rather than dimming the star, it acts like a lens, briefly amplifying and distorting the light, revealing the interloper's mass and motion. When microlensing occurs, a star's background light warps and brightens as the intervening mass crosses near our line of sight. This spatial distortion creates a unique signal, pinpointing the planet's mass and speed. It's handy not just for star-bound exoplanets, but also for free-floating rogue worlds. A prime example is the farthest exoplanet found by the Kepler telescope, 16,960 light-years away, a near twin to Jupiter. Each method has its strengths and quirks, but together they've unveiled countless exoplanets and promise even more revelations ahead. This cosmic exploration ties back to gravity's relentless pull, orchestrating motions from Earth's daily twirl to the local group's grand sweep through space. It's a reminder of how interconnected our universe is, every spin, orbit, and drift shaped by the same force. As we've peeled back these layers, from galactic mergers to exoplanet hunts, we've glimpsed the vastness of it all. And yet, there's so much more to discover, a thought that keeps the wonder alive as we gaze up at the stars. Things get really fascinating here. Once upon a time, we assumed our solar system was a standard model, with planets neatly sorted into 2 or 3 types. We figured there'd be rocky worlds like the 4 inner planets we know, Earth and its neighbors, and then the gas giants resembling the 4 outer planets in our system, with some further splitting into groups like Jupiter-like giants and icy behemoths such as Uranus, Neptune, and depending on who's counting, maybe Saturn too. But now, with over 5,000 confirmed exoplanets, and just as many candidates waiting in the wings, we've earned the right to rethink those categories. What we've discovered is that most of these newfound worlds don't fit neatly into either box. They land somewhere in between. They're heftier than Earth, but lighter than Neptune or Uranus, with sizes that fall between those two benchmarks. These planets tend to stand out with their greater mass, shorter orbital periods, and a haphazard alignment relative to our viewpoint. Many of them are likely mini-Neptunes, rather than super-Earths, though we'll need more research to pin that down for sure. Another surprise came when we found gas-rich exoplanets, orbiting astonishingly close to their stars, closer than Mercury hugs the Sun. That revelation introduced us to the hot Jupiter class. Truth is, exoplanets seem to be everywhere. Astronomers, though, naturally gravitate toward the spots where they've logged the best and longest observations. Take the Kepler telescope, for example. It served us faithfully for just over 9 years. For 3 of those years, Kepler locked its gaze on a single patch of sky, peering down one of our galaxy's spiral arms. During that stretch, it tirelessly monitored about 150,000 stars at once, and roughly half of all known exoplanets trace back to that region. Right now, you'd see a timeline animation on screen, showcasing all the multi-planet systems that this iconic telescope uncovered. There are also smaller batches of transiting exoplanets picked up during briefer searches by missions like K2 and TESS, the latter of which is still chugging along. Then there's a hefty group of exoplanets closer to the galactic center, spotted more recently using a method called microlensing. Believe it or not, figuring out how common these worlds are is trickier than it sounds, not because we're wildly unsure how many stars have planets or even the average number of planets per system. Sure, there's some guesswork there, especially since our understanding of the outer reaches of planetary systems is still so patchy. To get a clearer picture, we'd need either a big leap in direct imaging tech or much longer, sharper observations of more systems using radial velocity or transit methods. Still, we can confidently say the typical star system hosts anywhere from 4 to 20 exoplanets, a relatively tight range. But what about planets that don't belong to any star system? That's where rogue planets come in, sometimes called free-floating or orphan worlds. These are interstellar objects with planetary mass, drifting alone without any gravitational tether to a star, hence the name. By the most cautious estimates, our galaxy might house thousands, maybe hundreds of thousands of these wanderers. We know precious little about how many failed star systems exist for every successful one. On the flip side, there's a ton of mass out there we can't fully account for. Are there heaps of giant planets, icy titans, Earth-like worlds, or ice-packed spheroids? Estimates swing wildly, from about as many as there are stars to tens of thousands of times more. Only cutting-edge microlensing studies will help us spot them. Over the past 30 years, we've glimpsed thousands of exoplanets, other worlds, and star systems. So can we say today whether our solar system is ordinary or somehow special? In terms of planet count, it's probably pretty average. But vast swaths of the exoplanet landscape remain poorly explored, especially the stats on outer planets in most systems. That said, we might be unusual in having a lineup of rocky, Earth-like planets in the inner system, followed by bigger, gas-rich ones farther out. Observations of other systems show giant planets parked in the inner zones aren't rare, they're downright plentiful. We've also noticed that super-Earths, a type of exoplanet, pop up all over the place in other systems, but are completely absent from ours. Then there are 2 standout quirks that make us a bit of an oddball. Our Sun outshines and outweighs 95% of the galaxy's stars, and about half of all stars are part of multi-star setups, unlike our solo act. I'm not even touching on life. That's a whole other can of worms, and who knows how many of those confirmed, unconfirmed, discovered, or undiscovered exoplanets might support it. Some we think are rocky and probably have thin atmospheres like Earth's. Astronomers reckon a few sit at just the right distance from their stars so that, if they're water-rich, Liquid oceans could pool on their surfaces. You could imagine some of these worlds once had conditions like Earth's long ago, or maybe even now mirror what our planet was like 4 billion years back. But most of the planets we found aren't rocky. They're more likely cloaked in thick gas layers. The few with solid surfaces probably resemble our Mercury more than anything else. A lot of these rocky finds orbit M-class stars, red dwarfs, cooler than our Sun. Given their short orbital periods, they're likely tidally locked to their stars, and those same stars might have stripped away their atmospheres entirely. So far, no atmospheres on these smaller planets have been measured, whether through direct imaging or transit spectroscopy. To sniff out biosignatures, or at least hints of life, on these worlds, we first need to push past our current knowledge gaps. As telescopes, like James Webb and Euclid, already online, join forces with upcoming giants like Plato, the Giant Magellan Telescope, the Extremely Large Telescope, and the Nancy Roman Space Telescope, our toolkit will level up. We'll be able to probe exoplanet atmospheres, snap direct images of planets closer to their stars, catch microlensing signals from tinier worlds, gather more stats, and pick up fainter radial velocity signals. Everything's about to get a major upgrade. We'll also figure out how low a star system's heavy element content can dip while still forming rocky planets, and sort out which worlds are super Earths versus mini Neptunes. The coolest part? By blending atmospheric clues from transit spectroscopy with direct imaging, we'll get sensitive enough to peek into the atmospheres of Earth-sized planets around other stars. Do they have atmospheres? Are there molecules like oxygen, nitrogen, water vapor, carbon dioxide, or methane floating around? Are there chemical fingerprints tied to intelligent life, like chlorofluorocarbons or industrial pollutants? It'd be naive to expect those signals to be common across the universe, but we owe it to ourselves to look as hard as we can. And to wrap up, no big revelations here. Anyone hooked on space already knows the answer to this one. Studying planets boosts our grasp of how they form, evolve, and the processes shaping them. That knowledge could spark leaps in astronomy, geology, and astrobiology. Naturally, digging into worlds beyond our own sharpens our understanding of Earth itself. By eyeing young exoplanets, we can better piece together what our planet was like in its youth and what might lie ahead. Exploring other worlds could teach us how to safeguard and sustain life here. Why else? Simple curiosity, it's a powerhouse driving progress. No two people on Earth are identical, and no two exoplanets in the universe are carbon copies either. From soil makeup to atmospheric quirks, to the gleam of distant stars, each is one of a kind. Expeditions to other worlds aren't off the table either, and the dream of colonizing distant stars, while still out of reach, hasn't faded away. For those unconvinced by all that, here's a down-to-earth perk. Exoplanet research often fuels tech breakthroughs. Think robotics and telecommunications. Their growth ties straight back to space exploration, including the hunt for these far-off worlds. Keep that in mind and don't sell science short. Personally, I hope one day we'll spot a world out there that shows us how to live better here. No senseless wars, no chauvinism or dumb propaganda, no hunger or territorial squabbles. Maybe there's a place that could nudge us toward harmony, respect, and care for our environment before it's too late. Here's a wild twist about the universe. Everything we know from everyday life on Earth, every proton, neutron, and electron in our bodies, our planet, our solar system, and even our galaxy makes up just a tiny sliver of what's out there. Toss in neutrinos, light, and black holes, and you've still only got about 5% of the universe's total makeup. The rest? That's dominated by dark energy and dark matter, with the latter being one of the biggest head-scratchers in astrophysics. Experts are pretty darn sure it's real. There's heaps of indirect evidence. But since we haven't nabbed a single particle to prove it, plenty of folks, from pros to skeptics, aren't sold. Without it, the universe would look totally different. How? Let's dive in. About 13.8 billion years ago, the Big Bang kicked things off. Particles and antiparticles popped into being, clashing and wiping each other out, turning into electromagnetic radiation. The early universe was so hot, dense, and energetic that protons and neutrons could team up to form the first elements. Without other ingredients in the mix, one thing called the shots on which elements would dominate before stars even showed up. The ratio of photons, light quanta, to baryons, protons and neutrons combined. Dark matter or not, that ratio set the stage for how much hydrogen, helium, lithium, and so on formed in that fiery Big Bang aftermath. But soon after, dark matter's role turns crucial. The early universe was almost perfectly uniform, with density pretty even across the board. Yet tiny imperfections, little ripples, started growing under gravity's pull, eventually birthing stars, galaxies, clusters, and bigger structures. After the recombination era, when matter became transparent to radiation, that freed up glow spread out, reaching us today as the cosmic microwave background. We can measure temperature differences between any 2 points in this relic radiation and see how those gaps shift with distance. Those collapsing ripples, dubbed baryon acoustic oscillations by scientists, leave their mark in this pattern. Once neutral atoms formed, radiation stopped pushing back, and gravity got to do what it does best, yanking every bit of mass toward every other bit. Gas clouds clumped, collapsed, and sparked the universe's first stars, just like they do in our dark matter-rich cosmos today. But without dark matter's extra gravitational oomph, those pioneer stars would have spelled disaster. Stars don't just shine, they blast out ultraviolet and ionizing radiation, hurl particle jets, and fling fast-moving matter via stellar winds. For those first stars, far beefier than today's, these effects were dialed up even more. Without dark matter, the combined punch of stellar winds and UV rays would have slammed, surrounding matter so hard it wouldn't just drift back into the interstellar mix. It'd break free from the massive star cluster that just formed, untethered by gravity. As those stars aged and died, most blowing up as supernovae, their ejected debris would zip off so fast that, minus dark matter, it'd escape the gravitational grip of the leftover gas cloud entirely. Unlike our universe, where stellar leftovers get recycled across generations, a dark matter-free early cosmos might have seen its first stars as a dead end. On smaller scales, that'd mean surviving planetary systems would be bare-bones simple. Without recycling elements from one star batch to the next, we'd lack the heavy stuff, like carbon, nitrogen, oxygen, silicon, phosphorus, and iron, needed to craft rocky planets in protoplanetary disks. Life as we know it, out of the question. The only planets that could have formed would be gas balls of hydrogen and helium. Without heavier elements to cool forming protostars, we'd have fewer stars today, but they'd be way bigger, averaging 10 times our sun's mass instead of the 40% it is now.